Hi all. Let us begin with the next two types of sampling techniques, which is natural sampling and flat top sampling. So let us begin with the natural sampling as a first thing. So we have to analyze the sampling process in a more natural way, as we have seen as a drawback in our ideal sampling that we cannot go for generation of train of impulse signals. So here we have to consider a train of rectangular pulses, which is xp of t. So what we are now going to do is we are trying to multiply the original signal x of t with the train of pulses xp of t. Each pulse here xp of t is having a width t and its amplitude is 1 over t. In the pulse train, if we look at, we are having the pulse width of each of the pulse as t and the amplitude of each of the pulse is 1 over t. Multiplication of this original signal x of t by your pulse train is looking like as if we are trying to open a switch and close a switch for a particular duration of time. Now we are considering the sampling frequency here fs, and its reciprocal time period between the samples is considered as ts. So for every pulse train that is going to start and end, the period of that particular pulse train is going to be ts, which is the time period between the samples. So the resulting data xs of t, we are going to call the resulting sampled output as xx of t, which is the product of your x of t and xp of t. The sampling here, we are terming it as, or we are calling it as natural sampling, since the top of each pulse in xs of t sequence, it is retaining the shape of its corresponding analog signal during each pulse interval. If you can see, the top of all these pulses at the xs of t is as good as or is same as the analog signal x of t, which means it is following the amplitude of that analog signal x of t. So for each pulse is obtaining the new value or the new amplitude value with respect to its original signal x of t. So the original pulse train, the periodic pulse train, you can see the pulse train which is available here is periodic in nature. If I want to express this periodic pulse train in Fourier series, it can be expressed as xp of t is equal to summation n is equal to minus infinity to plus infinity cn e to the power of j 2 pi n into fs into t. So this is what is the expression of the pulse train in Fourier series, and the sampling rate here, as already told, it is considered as fs is equal to 1 over ts, which is chosen to be equal to twice that of fm. So we want to follow, for this case, let us follow the Nyquist criteria, that is fs is equal to twice that of fm, so that or such that our samples are lying just beside each other when it is being constructed. We can look here the magnitude of the spectrum. The magnitude of the spectrum of the pulse train is being visible here as a dashed line, and it has got the characteristic shape like a sync signal. So why is that sync signal? Is because we can try to bring this or convert this pulse expression, Fourier series expression Cn e power j 2 pi n into fs of t, and try to bring this in terms of our Fourier series. It will follow the sync expression, which is sinc of y will be equal to sinc of pi y divided by pi y. So that is what is being done, and we are going to get that expression in terms of sinc, and it is going to follow the shape of a sinc or follow the characteristics of a sinc. So now let us look at how do we get that excess of f, the final output in terms of the frequency. So we have the s of t, which we know we have considered it as to be the product of x of t into the xp of t, which is the pulse train. And the pulse train in Fourier series, we are trying to represent it as um, xp of t, which is equal to n uh, summation n tends from minus infinity to plus infinity Cn e to the power of j 2 pi n fs into t. So now we have the sampled output, which is basically given as x of t into summation n is equal to minus infinity to plus infinity Cn e power j 2 pi n fs into t. So considering that, what I can do is I can take this x of t term inside the summation, which will be as x of t into Cn e power j 2 pi n fs into t. The sampled waveform, which is x s of f, is found as f of summation n is equal to minus infinity to plus infinity Cn x of t e power j 2 pi n fs into t. Here if I would like to interchange the operations of summation and Fourier transformation, this is the Fourier transformation symbol which we have. If I would like to interchange the Fourier transformation symbol, then it would be summation n is equal to minus infinity into Cn f x of t into e power j 2 pi n fs into t. So using this frequency translation property, using this I can write this in terms of the frequency translation property of Fourier transform, which is basically written as x for the convolution of two signals, which is x of t into e power j 2 pi n fs of t is nothing but I know it is the impulse value, or it is the impulse response of a Fourier transformed signal. So that when I take the convolution of both of the signals, I am going to write that as a frequency with the help of the frequency translation property. I will be getting the value of x s of f, which is summation n is equal to minus infinity to plus infinity Cn x of f minus nfs. On similar lines with that of the unit sampling case that we have seen already. So here the x s of f, this particular output signal is nothing but it is the replication of your x of f signal, which is repeated periodically um, with a frequency fs hertz. So the same signal x of f is getting repeated here again and again with the frequency fs hertz. So in this, what we can see is the Fourier, the x s of f is the weighted pulse train due to the series coefficients that are available, like c naught, here it is c1, here it is c2, c minus 1, and then c minus 2. So the amplitude of the x of f signal, which is at the output as x s of f, but now the amplitudes are the Fourier series coefficient weighted pulse train, which is represented here as C0, C1, C2, and C minus 1 here, C minus 2 here, but all of them are due to the Fourier series weighted value. The variation in the amplitudes at Fs or at 2Fs or at minus Fs, minus 2Fs, what we are observing is due to the coefficient as earlierly said. So which is similar or which is going to be constant in case of the ideal sampling process what we have seen earlier. So in impulse sampling or in ideal sampling, we saw that the pulse which was being generated, it was almost having an ideal pulse amplitude here. So instead of that, here we are going to have the Cn, which is the Fourier series coefficient value. And you can also see that the pulse width is t. It is actually satisfying that in the limit, as the pulse width t tries to approach to 0, as the limit t tries to approach to 0, Cn approaches to the value of this coefficient approaches to 1 over Ts, which is much required for us. When does it approach 1 over Ts? It is going to approach for all values of n, that is for all the values of n like 0, 1, 2, 3 and so on, which means I can generate such kind of signals, I can generate such kind of pulse transmitted or digitally transmitted signals due to the presence of or due to the functioning of such kind of sampling theorem, which is going to hold good even for natural sampling as well as for the ideal sampling. The only drawback that we have come across here is we are trying to have the train of pulses and we are trying to generate the signal. So now for whatever we have generated the signal here, it is for perfect sampling or it is for Nyquist rate, which is Fs is equal to 2 times of Fm, where I can see the pulses are being placed close by to each other, close to each other. So hence the reconstruction is also going to be very easy for us. Now the same process what has been done is being given here in steps, where we have considered a pulse of width Ts, its amplitude is 1 over Ts. We have seen that xs of s is nothing but it is the replication of x of f, which is periodically repeating for every fs hertz, and the width of that particular xs of f is dependent, or its amplitude is purely dependent on the value of Cn, which is the weighted value of the Fourier series coefficient. So now what is one problem that we are observing practically to implement natural sampling is also possible. So sometimes this natural sampling is also called as practical sampling. So this natural sampling has a problem. What is the problem is that it takes the value, or it stops of samples, uh, follows the values and follows the values of a pulse, which is almost going to traverse the original signal like this. It is not going to be an individual pulse value. Instead it is going to be a flat top sampled values which it is going to carry. So as you can see here, it is showing us there are flat edges or flat tops of the pulses which are being followed by these pulse train when we multiply this pulse train with that of the x of t signal. So this flat top which is present for a sample here, so this particular sample, it can generate infinite number of possible values. When we go for quantization process, this particular thing, it can generate infinite number of possible values, but we don't want to end up with a problem there in generating many number of values. Instead we want one single amplitude value. That one single amplitude value we can achieve by the another technique which is called as flat top sampling. So to overcome this particular case of uh, pulses or samples taking the flat tops, and or it is taking more number of amplitude samples or more number of amplitude possibilities, so we want to avoid that. So that is overcome in flat top sampling, and this is also called as sample and hold operation, or this technique is used to realize sample and hold circuit. Why the name sample and hold is because we are going to make use of a switch and a capacitor. The capacitor is responsible for storing the value, and the switch is, or the transistor is responsible for switching purpose on and off of the particular transistor. So in your sample and hold, the input is continuously sampled and then the value is held for a long, as it takes for A to D converter, that is analog to digital converter, it acquires a value. It acquires one single value. So now let us look at, to overcome this drawback, now let us look at the next kind of flat top sampling, which is given as x of x dash of t. Please note it is x dash of t, and then is being flat top sampled with the pulse train p of t, or multiplied with the pulse train p of t to get the samples xs of t. What is this x dash of t? This x dash of t is nothing but it is my earlier natural sampling process which we have done. That is, it is going to be x of t into xp of t for the same pulse train. Now I am taking up, or now I am taking one more pulse train which is p of t to generate my new sampled value xs of t. So that signal we are assuming here it as s of t. So you can see the pulses which are being present here. The pulses here are exactly taking only one single value. It is taking only one single short value here. That is absolute value. It is not carrying too many number of values. If I try to trace such kind of pulses, it is actually flat. So only at those flat regions I am going to take up the value. So the flat top sampling that we have considered here, the pulse width is t, and the sampling period is ts, and then the signal that we have considered is s of t, and the message signal we have taken it as m of t. So the major thing about the sample and hold circuit, or the flat sampling process that we are presenting here, is it is going to give us a good sample value, or it is going to give us a good amplitude value of the particular sample that we are trying to consider. One question, one question that arises: why do we need the flat top sampling? It is during the transmission that we have observed noise is introduced at the top of the transmission pulse, which is easily removed, or which can be easily removed if the pulse is in the form of a flat top. So that is what I said, it is not going to carry, or it is going to carry too many number of amplitude values, all possible values of amplitude in case of natural sampling. So in order to remove that kind of all possible values, here we are trying to flat the top of the sample. So flat the top of the sample means it has to take only one flat value. It has to be flat like this, even though the message signal is passing by. It should not trace the amplitude or the message signal path. So here the top of the sample is basically made flat. They have constant amplitude. So because of which the name came into existence as flat top sampling, which makes use of sample and hold circuit. If I try to represent the same flat top sample in terms of, or in case of my frequency domain signal, so this would be the frequency domain signal which is going to exist. So I'll be having my original message signal present here, and then I'll be having the next higher set of frequencies which are going to be present, like in the case of natural sampling. So the higher frequency component amplitude is going to reduce here. The amplitudes of the higher frequency component, if this is at 0 frequency for my message signal, then this would be at my fs, and this would be at my minus fs. So the amplitude of this signal is going to reduce in case of flat top sampling. That is because of what is called as aperture effect. It is due to the aperture effect that is present in flat top sampling. So what is this aperture effect is? I told the amplitude of the signal is going to reduce. Amplitude of the signal is going to reduce is nothing but is going to this results basically in the attenuation of the higher frequency components of the message signal, or the higher frequency components which are present along with the message signal spectrum. So thus the sampled signal is in the flat top sampling consists of attenuated high frequency component, and this effect is known as aperture effect. The attenuation is more, which means the higher frequency components are going to get suppressed, which results in what is called as aperture effect. So it is very important to know that it is due to the presence of the transistor and the capacitor that we are trying to make use in the sample and hold circuit, which results in aperture effect. So next we have the next concept, which is called as aliasing. So we have already come across the aliasing effect, which we have seen. It is nothing but we have seen that two signals are getting overlapped whenever I consider my frequency fs to be less than twice that of FM, less than twice that of 2 FM. So which is nothing but undersampling case. So in that case, I can see the higher frequency components getting overlapped with my original message signal. So that should not happen. So in order to avoid that, we are looking for which will be the best suited frequency, or which would be the best suited sampling frequency that we have to consider along with the frequency of the message signal. How does or when does such kind of aliasing effect comes into picture is whenever I consider my sampling frequency, to be less than twice that of FM. This is what does it is going to do is it is not going to distort, or it is going to compress, or it is going to overlap with the other sideband signals which are present, and wherein we as a user, or we as a signal processing engineer, we will be unable to differentiate between the signals, as it becomes indistinguishable, or we cannot separate out and say that this is signal number 1, signal 2, signal 3, signal 4. So this becomes difficult for us to indistinguish from each other during the sampling process. So at that instant we come across what is so called as aliasing. So this aliasing can be removed by making use of the aliasing filters. Other than aliasing filter, how at the very beginning itself we can take care that the sampling is not going to create such kind of error, or create such kind of effects, is we have to consider a perfect sampling, or what is also called as Nyquist rate, which is fs is equal to twice that of fm, wherein we can see there is clear distinction or clear differentiation can be done between each one of the signals that when we are trying to reconstruct the original message signal. So we have also seen the oversampling case where fs is greater than twice that of fm. So when it is greater than twice that of fm, we are going to actually waste the bandwidth, or waste the frequency that is going to be present between each one of the signals, which are spaced apart as fs, 2fs, 3fs, or minus fs, minus 2fs, and so on. As an example, if I am considering an audio signal with a bandwidth of 20 kilohertz, it must be sampled at least at 40 kilohertz to avoid the aliasing. If I am considering an audio signal of 20 kilohertz, it must be sampled at a rate of 40 kilohertz in order to avoid the aliasing effect. That is when we consider, or when we say we are holding good with the Nyquist rate, or with the perfect sampling process. So the same thing which is present here is the aliasing effect. Like what happens to the low pass filter when it wants to actually reconstruct. If it is there with my Nyquist rate, it is very easy for the low pass filter also to have the bandwidth limitation being done, and within that bandwidth I can reconstruct the original message signal. But if it is in case of my frequency which is fs greater than twice that of fm, which we call it as oversampling, in this case I am going to have the bandwidth which is being present. Even in this case we can actually reconstruct back the original message signal, but it is the wastage of the bandwidth that I am trying to do, or the wastage of the frequency that we are going to incorporate here. When it comes to the frequency that we are trying to consider fs to be less than twice that of fm, that is what we call it as undersampling. So in this undersampling we have seen the effects of aliasing, that is we cannot distinguish between the two consecutive signals. So coming to the summary of today this session, we have studied about the natural sampling, and then we have looked into the disadvantage that was caused in natural sampling, went for sample and hold operation, or which we also call it as flat top sampling. And then flat top sampling is the most practical one, including your natural sampling, but always the most practical one to be considered is the flat top sampling by making use of sample and hold circuit. And then we have the last topic that was discussed. We should always have the frequency to be considered exactly at Nyquist rate, which we said as fs to be equal to twice that of fm, or even it can be fs greater than twice that of fm, in order to avoid the aliasing effect which was caused and in the underdamped sampling. So that's about the summary of the topics that was covered so far. Thank you. Happy learning.